Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to continue our chapter on spans, right? So last time we talked about what is the intuition behind spans, what is the mathematical definition behind spans, and all of that good stuff. So now we're going to go and actually do the theorem now. So the theorem tells us if we let u sub 1 u sub 2 all the way to u sub m, as well as the v vector. So these are all in Rn. Then v is an element of the span, or it belongs to the span of u sub 1 all the way to u sub m. If and only if the linear system with, or it has this specific row in an augmented matrix. U sub 1, u sub 2, all the way to u sub m is v. The thing has a solution, right? So this is another way of saying we can write v as a linear combination of u sub 1 to m, because here it's an augmented matrix. And if we do row echelon form, we're going to see a solution, right? Okay, let's actually copy this. Okay. I'm going to put in my, or one of my definitions here. Right. So what's the proof behind this? So the proof, or the why behind it, seeing that the vector v is part of the span of u sub 1 to m, if and only if there exists scalars x sub 1 all the way to x sub m that satisfy this equation. X sub 1, u sub 1, all the way to x sub m, u sub m is v. So again, it's that linear combination idea. We can write v, the vector v, as a linear combination of all of the vectors that are part of the span. Then if we can, then we know v is part of that span. And again, it's only true if and only if the corresponding linear system has a solution, right? So we can write it as this, and the corresponding linear system has a solution. If it has a solution, then we know that we can put scalars in there, and we know we can write a linear combination. That's it. That's the proof. Now let's ask this question. When does the set, or a set, when does a set actually span in Rn? When? And what occurrences will it actually span? Well, based on the examples we've seen, a set of 2 vectors spanned R2, a set of 3 vectors spanned R3, but here's the example, and it actually gives us a very interesting question. Is it always true that a set of n vectors span Rn? Is it a fact that there's a correlation between the number of vectors and its span to the number of dimensions, right? Because here we've been noticing that some vectors u sub 1 to m in Rn, but we're not writing n. Here we're not writing n, we're writing m, right? So is there some correlation between the two? Well, not always. That's the answer. I'm just gonna blurt it out, not always. So, for example, say here we have 2 vectors, right? V sub 1 is 1, 1. V sub 2 has components 2, 2. So these are 2 vectors. So they must span R2, right? Well, if you think about it, the span of these 2 things is a line, since V1, or actually V2 in this case, is actually just twice of V1. So these are scalars of each other. You can multiply 2 to V1 to get V2. So they are literally spanning the same line. So this is the span of this thing. It's a shape, yeah, but it's a line. To be more mathematically precise, it's a line in R2, right? So from there, the span of u sub 1 and u sub 2 is not all of R2, right? Here's the nice example, or a nice geometric intuition behind it. So this is the span of v sub 1 and v sub 2, right? It's a line. It's not the whole plane, the whole 2D plane, the XY plane. It's not all of that. Okay, here's a more interesting example, right? So a more subtle example. So this one's not super obvious, because the first one is obvious. So here we have 3 vectors. We have u sub 1, which has components 2, 1, 1. We have u sub 2, which has components 1, 2, 3. And we have u sub 3, which has components 1, -4, -7. So we can't say that although we have 3 vectors, that doesn't mean they span R3, right? But here, funny enough, u sub 3 is a linear combination of u sub 1 and u sub 2. So you can check me on this, but this is true. Oh, that's minus. So u sub 3 is a linear combination of vectors u sub 1, u sub 2. So u sub 3 is part of the span. Okay, I'm just connecting ideas here of u sub 1, u sub 2. Right? So what is the span of those three things? Well, here's the thing. Any vector that is a linear combination of u sub 1, u sub 2, and u sub 3 can actually be expressed as a linear combination of just u sub 1 and u sub 2. So what are we saying here? Okay, mathematically, let's do it mathematically. If we do a linear combination of u sub 1, say we have x sub 1 here. The x's are scalars, plus x sub 3, u sub 3. This is the same as this guy, the linear combination of only two vectors. And so what does that tell us? That tells us the span of u sub 1, u sub 2, u sub 3 is actually the same span of u sub 1, u sub 2. Right? Just a fun fact here. Okay. I'll let that sink in for a bit. Now, since we have already shown this in the previous example where the span of two vectors is not R3, that means the span is also not R3. The span of these three vectors is not R3. Right? What example was this? 3? Oh no. Oh, I did show it in example 2. Oh, here. Yeah. No solution. Example 2. Oh yeah, this one doesn't span R3. Okay. Oh, so that the spans of these are equal. In the previous example, we know that the span of this thing is not R3. But since these two are equal, that means the span of u sub 1, u sub 2, u sub 3 is also not R3. Right? We did show this. So what does that mean? If we have linear combinations such as these, then and we know what their span is, it's not going to be all of R3. Right? But this is a very non-systematic way of doing it. It's more like finding information from one thing and then proof by contradiction. But here, yeah, we're going to a topic soon where we actually get to do a systematic way of determining whether vectors are in a span of R3. Right? Okay, let's see. So let's go through another theorem here. So theorem 2.7 tells us, so we let u sub 1, u sub 2, all the way to u sub m. And I'm guessing and u. These are vectors in Rn. Now, if U is in the span, so I'll write it mathematically, this weird looking E thing just means it belongs to. So it belongs to the span of U sub 1, U sub 2, all the way to U sub M. Then we say that the spans of the two are equal. So the span of U sub 1, all the way to U sub M is the same as the span of U sub 1 all the way to U sub M. That's the theorem, right? Okay, let me quickly take a screenshot. Not screenshot, like a copy paste thing. Because I'm trying to put all of the theorems in one place here. Right. Okay. Going back. We know this is true. Okay. Do a proof. So the proof is, yeah, what's the proof here? Let's store them in variables. Let's say S is not be the span of U, the one with U, and let's do S sub 1B, the span of the vectors, the set of vectors without U. Okay. And then we need to show, S naught is S1. So how do we do that? We can write linear combinations. Okay. So let's try this. Suppose V sub 1, or no, not V sub 1. We can just do V actually. Suppose V belongs in S1. So let's say this is true, right? We can write U sub 1 all the way to U sub M as a linear. We can write V, vector V, as a linear combination of U sub 1 to U sub M, right? Then there exists scalars. So we say, let's do A sub 1 all the way to M. Now I'm going to do X this time, such that V, the vector V, is equal to A sub 1 of U sub 1, A sub 2, U sub 2, all the way to A sub M, U sub M. The same thing as 0 of U, because this is equal, right? A sub 1, U sub 1, all the way to A sub M, U sub M. Now what? What's happening here? Here we can say that the vector V is also in S naught. It's also part of S naught. So S sub 1 is a new term, a subset of S naught. Right? Now, suppose V is actually an S naught. And then we have a bunch of scalars here. Okay, let's see. So again, we have scalars. Let's do B this time. Let's do B naught, B1, all the way to Bm, such that we can write a linear combination of V as B naught U plus B1 U sub 1 all the way to Bm U sub M. Now since U, okay, now this is getting complicated. U is an S1, right? We said it's an S1, S sub 1. Or that's what we're claiming. Then there exists scalars C. Okay, now we're doing C. Such that, okay, can we put this all together? The U is actually a linear combination of these guys. Okay, I'm waiting for it to be together. Then we say that, so V is B naught of U. In this case, we replace it with the linear combination itself. So U sub 1, C, M, U sub M. And we continue adding it, B1, U sub 1, all the way to Bm, U sub M. And then what do we notice here? We're actually multiplying B naught to all of these guys, right? So we're multiplying B naught, C1, U, or no, not U, plus B1. Oh, okay, and then, or is it B naught? No, it's not. Cool. B naught. There we go. Then we keep going. So this is B naught C2 plus B2. Okay, it's getting a little bit tricky here. U sub 2. Then we keep going. All the way to Bm. No, still B naught. Cm, Bm, U sub M. Okay, what does this tell us? These are just numbers. All of these are numbers. Here we can see that V can be written as a linear combination of U sub 1 to M. Still doesn't tell us that the span of those two are equal. Oh, here's the catch. Thus, V is part of S1, right? So S naught is a subset of S sub 1. Since S naught and S1 are subsets of each other, S naught is S1. That's the proof. That was not fun. Okay. do an example. Do example 5. So here we're being asked to find a vector in R4 that is not in the span of U sub 1, 2, and 3. Can we do that? Here's the given. U sub 1 is 1, -2, -1, 2. U sub 2 is -3, 7, 4, -6. U sub 3 is, okay, these are the components. 2, 0, 2, 5, 20, 25. Okay. Anyway, so can we find a vector in R4 that's not part of the span? Meaning, what does that mean? We cannot write that vector as a linear combination of these three. Okay? What we can do though is we can do our usual matrix, augmented matrix, but we're not going to do it with the constants, right? So I'm going to say, so say this vector is a V. So V cannot be a linear combination. Let's do X. Right? So we do our usual augmented matrix. 1, -2, -1, 2. Then -3, 7, 4, -6. Lastly, 2, 0, 2, 5. We don't do anything here, right? So we just do that. Then when converting it to row echelon form, here's what happens. 1, -3. Okay, I'm copying the textbook here because I don't want to do this on my own. 0, 1, 4, 0, 0, 1, 0, 0, 0. So this is an echelon form because the pivots are all, well, they're there. They're 1. Okay, it doesn't matter if they're 1. What matters is the leading variable is this downward staircase thing, and the 0 row is at the very bottom. So we know this is an echelon form. It's not reduced, but it's an echelon form. Great. How do we find a vector that doesn't equal this? Well, we can say, so V could be 0, 0, 0, 1. Since it would look like this. 1, 0, 0, 2, 4, 1, 0. Then we do 0, 0, 0, 1. Which has no solutions. So V cannot be part of the span, or it cannot be written as a linear combination, so it can't be part of the span of these three things. These three vectors, not things. Okay? Cool. Okay, that's one of them. Another theorem. Okay. We're really getting bogged down on these theorems here, but we'll fight through it. Right? I put this here. Hopefully I did. If I didn't, that's a bummer. Oh, I did. Good. Okay. Let's do one theorem here. I think this was 2.8. Okay. So what does it say here? So suppose u sub 1 all the way to m is in n-dimensional space. It's in Rn. And we let this augmented matrix be, so say A has this matrix u sub 1 all the way to m. And this is approximately B. And B is an echelon form. So what does this tell us? Then the span of these vectors, u sub 1 all the way to m, is exactly Rn. If and only if B has a pivot position in every row. So if B is an echelon form, it has to have a pivot position in every row. That means it has to have exactly one solution. And if it has to have exactly one solution, oh, that's interesting. Why is it in Rn? Did we do that here? This doesn't have a pivot position in every row. Doesn't have a pivot position here. That's interesting. Okay, let's see. Let's actually look at this one carefully. This one, I think, is somehow not connected to the ones we did. Somehow not connected, but it is still kind of connected. Let's see. So apparently, if we have a pivot position in every row, say B, and it's in echelon form, then we will have one exact solution, right? Because there won't be any free variable if we have a pivot in every row. What else does that tell us? Anyway, let's see. So we have a proof here, which I am going to go through. So the proof tells us, okay, suppose B is an echelon form, right? And let's say, okay, let's say it has a pivot position in every row. Oops. In every row. And then we consider the augmented matrix, which is u sub 1, u sub 2, all the way to m. Then this gives me a vector v, some random vector. We know that v belongs in Rn. Say that's true, right? Now, since B has a pivot position in every row, the same sequence of row operations that transformed A to B will transform to echelon form with no pivot position in the last column. Wait, so let's say we have an original matrix A, but since B has a pivot position in every row, same sequence of row operations to transform A to B will transform to echelon form. B has a pivot position. Wait. uh, it's saying, why am I not getting this? This B has a pivot position in every row. Here's all my definitions. What does it mean to have a pivot position again? Reduced. Oh, system. Echelon. Reduced. Oh, it's not here. Okay, it's in chapter 1. Probably. Probably here. Homogeneous. Backward. Pivot. Okay, it's here. Contain leading term in a matrix. Okay, let's see. So it's telling us that since B has a pivot position or a leading term in a matrix, so it has a leading term in every row. That's what it's saying. Same sequence of row operations that transformed A to B. So what it's saying is that B will have no pivot position in the last column. Wait, if it's an echelon form, it doesn't have a pivot position in the last column. Oh, it doesn't. This one doesn't. But I think most of them do. Like, let's say, where are the examples? Say this one. It has a pivot position at the last column. Last column here is 3. What does this mean then? If we do I did my elementary row operations, and it says it has a pivot position in the last column, rightmost column. Okay, it's just confusing me. I would just say something like, if we can get the row echelon form, and there is an exact solution, then we know it's always going to have a solution, right? So therefore, doing back substitution always, that's interesting, always yields or it will always give us a solution regardless of V. And so by that, the span of U sub 1 to M is the whole Rn. Now suppose, okay, so it's not completed proof. Okay. If there's no pivot position in the last one, then that's probably a 0. I'm gonna assume that's a 0 row. So it's always gonna have one exact solution. And if it has an exact solution, regardless of V, span is in Rn. Right? Now, suppose B does not have a pivot position in every row. It's still an echelon, right? Which implies the last row of B is zeros. And since the last row of B is zeros, corresponds to a system with no solutions. What? Last row of B is zeros. That doesn't say that. No, actually, it kind of does. Oh, it is going to be no solution. Yeah, right. Unless B is a zero vector. So now, suppose B does not have a pivot position in every row. So last row is zeros, right? Then if we let V be 0, 0, 1 in Rn, and we consider this augmented matrix, say this is B, this is V. And since the last row of B is zeros, this has no solution. It's an inconsistent system. Right? If it has no solutions, then it's not linear combination. So V is not in that span of U sub 1 to M, which is not Rn. Why? Because V is in Rn, but it's not in the span, so the span is not Rn. Okay? I hope that made sense. Lots of proving here, but I hope that made sense. Okay, we have a couple more to do. Actually, it should be light. Then I'm gonna take a break. Okay, so let's do example 6. Oh, did I put this proof in here? Okay, good, I did. Right, so example 6, we want to determine if the span of 4 vectors here, U sub 2, 3, 4, actually it's fine, is in R4, I'm guessing? R3. Yeah, so we already know there's no correlation to the number of vectors to its dimensions. It's only the number of components of each vector that correspond to the dimensions. Where, okay, now we write out what each of these are. Since it's in R3, we're gonna have 3 components, right? Okay, 2, -1, 2. Then use of 3 is something like -2, 5, 10. Then use of 4 is 3, -4, 8. So we have these 3 vectors. Are they in R3? How do we know, right? So based on that theorem that we did here, we want to make this in echelon form, say B, if we have a pivot position in every row. So we have to have a pivot position in every row. Okay? So to check, we make an augmented matrix. And check for if there's a pivot position in every row. After doing all of those Gaussian elimination, all that stuff, right? So let's actually check. So here I make an augmented matrix, or not necessarily an augmented matrix. I make a matrix. 2, -1, 2, -2, 5, 10, 3, -4, 8. And this is equivalently, so the matrix in reduced echelon, no, in echelon form, this is 1, 0, 0, 1, 0, 0, 0, 2, -2, 3, 3, 1, 3, -1. What do we notice? There is a pivot position, but not in every row, right? And if we look at our proof here, let's say there's no pivot position in every row. The last row is zeros. So this doesn't span Rn. So there's no pivot position in row 3. So span is not Rn. Right? Span of u sub 1 to 4 is not R3. Okay? It's as simple as that. Okay. That's a very interesting theorem, right? Since from that theorem, we can tell if the set does not span Rn. Okay? Right, let's do theorem 2.9. We can fight. Yeah, we can do this. Hopefully. Yeah, we're pretty close. So we should be fine. So for theorem 2.9, we let u sub 1 all the way to m be a set of vectors in Rn. here's the thing. If M, the number of vectors in the set, is less than n, then set does not span Rn. If the number of vectors is less than the number of dimensions, it doesn't span Rn. Right? Well, this one it's more, so we actually don't know. But for sure we know if it's less than, doesn't span Rn. Oh shoot, no, my bad. Yeah. If it's greater than, it might or might not span Rn. So this one, there is no correlation to when m is equal to or greater than n. So we cannot really say. Okay. Right. So I'm gonna put it here. Another theorem. Right. That's just so no more proofs here. Hopefully not. Oh, proofs are so tiring. Let's talk about the equation ax equals b. So what is that? So by now we are comfortable with translating back and forth between vector equations and linear systems, right? So here we give a new notation that will be used for a variety of purposes, including expressing linear systems in a familiar form. Okay, so we let let's try this. We let A be a matrix with columns A sub 1, this one being equal to 10, 5, 7, and A sub 2. Uh-oh. This one being equal to 8, 6, negative 1. So A is just, so these are vectors actually. This is just this matrix. It's a 3 by 2 matrix, right? Also, let X, which I'm assuming is a vector. So we have components X sub 1 and 2. So the product, so A, or actually just do it down here. So A X is just this thing added or multiplied to this thing, which is just X sub 1, A sub 1, X sub 2, A sub 2. So again, we can see it's a linear combination, right? So we say from here, AX is a linear combination of columns of A. You can think of the columns as vectors, to be honest. With scalars, but the scalars here are expressed as components of X, right? Next, we let a B vector have these components 18, 3, or 31, 3. Then this AX equals B is a compact form, is a compacted way. It's a compacted way of saying of X sub 1 plus X sub 2 is equal to B, right? Which in turn gives us a linear system. So now we have three ways to express a linear system. So we can either do it using AX equals B, we can do it as a linear combination, or we can do it as a linear system, pretty much. Linear system, AX equals B, linear combination, augmented matrix, vector equation. Lots of ways to do it, right? It's really just which one you like the most. Okay, let's look at the definition here. 2.10. Here we let A sub 1 all the way to A sub n, or m, my bad, be vectors in Rn. Okay. If, say, A is this humongous thing, A sub 1 all the way to A sub m, and X being X sub 1 to m, then AX is it's just a linear combination, right? Oh no, now I'm okay, I'm dizzy. Okay. Yeah, I think I can copy this. Let me put here. Nice. Put it up maybe. Okay. We So remember, the product AX is only defined when the number of columns of A is equal to the number of components or entries of X. Right? We can't do it when there are more components of X and lesser components of A, or lesser vectors of A, column vectors of A. Right? Okay, let's look at. Okay, I'm not gonna do this anymore. It's okay. Suppose. Okay, actually, we can do it. Translating the system. Yeah, example 7 is more about translation, so I'm not gonna do that anymore. Example 8 is a bit interesting. Oh no, A is just combining stuff. Yeah, it's just combining stuff. It's okay. I'm not gonna do it anymore. Let's move on to a new theorem. This is 2.11. Here we let no proofs, please. I don't like proofs. So here we let a sub 1 to a sub m and b. These are all apparently vectors. These are vectors in Rn. Then the following statements are equivalent. That is, if one is true, and so are the others. If one is false, then so are the others. If one is true, all are true, and vice versa. If one of them is not true, then all of them are not true. Okay, so a statement here is that B is part of the span of A sub 1 to M. That's true. B, this one, X sub 1, A sub 1, all the way to X sub, not 2, X sub M, A sub M is equal to B, has at least one solution. And if it has, then it's in the span, right? C, this is literally the same thing as the letter B, but the vectors here, it's an augmented matrix, has at least one solution. So this is the same as B, it's just an augmented matrix. And so if the two are true, then A is true. D, AX equals B has at least one solution, which is the same as C. It's just a more compact way of writing it. Yeah. So really, B, C, and D are pretty much the same thing. It's just three different ways of expressing the same thing. And if those three or one of those three are true, then the rest are true. Or even if A is true, then the other three are true. B, C, and D are true. Okay, let's continue. So this theorem actually follows directly from the definitions. So the proof is left as an exercise. I'm not going to do the proof. But the result is not hard to arrive at. And it is important because it explicitly states the connection between these different formulations of the same basic idea. So as a quick application, note that vector B is in the span. So we can write a linear combination of it. It's one solution. If there are no solutions, then it's not part of the span, right? So, okay, here are just some examples of what that looks like. So those ideas come in hand in hand. So this is an example of all three being there, right? Here we see that, so if we look, we see that B, vector B, geometrically, just looking at it geometrically, you see that B is actually part of the span of A1, A2. Right? What else can we say? So if it's part of the span, we can write a linear combination that has an exact solution. Another way we can do it. Oh, why am I doing that? 2, 8, oops, 8, 2 has at least one solution. AX equals B has at least one solution. So these four are true, right? Now, a case where this is false is this thing here. This is a case where this is false. So B is not in the span of A sub 1, A sub 2. You can't write this thing or B as a linear combination. There is no solution. And so the rest are false. Rest are false. Yeah, so that's it for this video. I hope you guys enjoyed and learned a lot, and I'll see you all in the next one.